polyomino of size n is an edge-connected set of n cells on the regular square lattice. Polyominoes, known as polycubes in higher dimensions, are studied in many areas, among them computational and discrete geometry, statistical physics, and recreational mathematics. Fixed polyominoes are considered distinct if they differ in their shapes or orientations. The number of fixed polyominoes of size n is denoted by a of n. For example, a of 2 equals 2. A of 3 equals 6. And a of 4 equals 19. In 1967, David Klarner showed that the limit exists. Lambda is known as Klarner's constant. It took 3 decades until Madras showed that the growth rate limit of polyominoes in the plane exists, and hence is equal to lambda. There have been several attempts to estimate lambda. Before the first work on polyominoes on twisted cylinders, the best known lower and upper bounds on Klarner's constant were: a mistake was found in the proof, and the lower bound turned out to be only about 3.87. By counting polyominoes on twisted cylinders, an improved lower bound of 3.985 on Klarner's constant was obtained. This is now the best known lower bound on Klarner's constant. A twisted cylinder of a fixed perimeter W is obtained from the integer grid by identifying coordinates of such form so as to create a spiral grid of perimeter W. Geometrically, the twisted cylinder can be imagined as an infinite tube. Here, the wraparound connections are indicated, so that cell WY is a neighbor of the cell 0y plus 1 for all values of y. In other words, it is like identifying these indicated cells. Without loss of generality, we label this cell 1, and so cell I is a right neighbor of the cell I minus 1. A polyomino on the twisted cylinder is a finite edge-connected set of squares of the lattice embedded on this cylinder. Polyominoes on twisted cylinders are relatively easy to enumerate due to the limit in the size of their boundary. This boundary can be cut by a boundary line, and the boundary cells are the W cells adjacent to the top of this line. The twist in the cylinder allows us to build polyominoes on the cylinder incrementally, one step at a time, through a uniform process. The polyominoes are built from left to right, adding one cell of the twisted cylinder at a time. The new cell is either occupied, that is, belongs to the new polyomino, or empty, that is, does not belong to it. A partial polyomino is the part of the polyomino lying above the boundary line at some moment. A partial polyomino is not necessarily connected, but it can become connected if enough cells are added so as to make the entire polyomino connected. The signature of a partial polyomino indicates to which connected components the boundary cells belong. When either an empty or an occupied cell is added, the signature is updated accordingly. For example, the boundary cells 1 and 3 are not in the same connected component. Therefore, they belong to different subsets of the signature. After adding an occupied cell, the partial polyomino is now connected. Hence, the boundary cells 1 and 2 become members of the same connected component. Therefore, they belong to the same subset of the signature of the partial polyomino. The key idea is that we don't need to keep in memory all possible polyominoes, but only all possible signatures. The process of counting polyominoes on a twisted cylinder can be modeled by a finite state automaton as follows. The states of the automaton are all possible signatures. The initial state corresponds to the signature that encodes W empty cells. Each state has up to W outgoing edges labeled 0 through W-1. Being at state Q, and upon reading the input character K, the automaton switches to the new state Q' that corresponds to concatenating to any polyomino with signature Q, an occupied cell, and then K more empty cells. Naturally, concatenating W empty cells to any polyomino would terminate it, since then any further occupied cells will be disconnected from this polyomino. For example, upon reading the following input characters, the automaton runs as follows. As we can see, a sequence of n input characters corresponds to a polyomino of size precisely n. In addition, any valid polyomino may end at the state corresponding to this signature by concatenating to it empty cells as needed. This state is the only accepting state of the automaton. In the automaton shown on the screen, this state is colored green. As a result, the number of polyominoes of size n on a twisted cylinder of perimeter W is equal to the number of words of length n that belong to the language recognized by this automaton. Obviously, this automaton can be described by a transfer matrix in which each entry, ij, contains 1 if there is an edge between states I and j, and 0 otherwise. It is guaranteed from Frobenius' theorem that this matrix has a unique positive eigenvalue which equals lambda W, the growth rate limit of polyominoes on the twisted cylinder of perimeter W. Frobenius' theorem also provides a constructive method for computing this value. It is easy to observe that this inequality holds. This follows from the fact that any polyomino on a twisted cylinder can be embedded in the regular plane. Therefore, Klarner's constant is bounded from below by lambda W for any value of W. Similarly, it is easy to observe that the number of polyominoes of size n increases as we enlarge the perimeter of the twisted cylinder. Hence, the larger the perimeter of the twisted cylinder is, the closer the growth constant of polyominoes on the cylinder to lambda is. Here are lambda 1 through lambda 23. Lambda 22 was computed about 6 years ago and was then the best known lower bound on Klarner's constant. Very recently we were able to compute lambda 23 and improve the lower bound to about 3.985. It is estimated that by computing lambda 27, the mythical barrier of 4 will be breached.